All right. Good afternoon, everyone. Thanks for coming. My name is Jimmy Bogard. I have to change this now because I'm not on Twitter anymore. So you can find me on Blue Sky at jimmybogard.com. I don't know how to say that, but that's my Blue Sky handle. This presentation, as well as the code example we'll be walking through later, is on my GitHub at github.com/jbogard. There's a presentations repository, and so that's where you find all my stuff there. I blog occasionally, less than I used to, at jimmybogard.com. And my day job is as a consultant. So a lot of things we'll be talking about today is from my experiences building complex distributed systems for teams and then having to deal with the messiness of those realities. Now, this talk is not going to be about consensus protocols, so things like Raft or, well, that's the only one I really know off the top of my head. This isn't about distributed systems in terms of a single database that's been distributed out, in more than one location. This is more about complex distributed systems where everything is its own little application doing its own individual job. I used to title this about microservices, but it really is not specific to microservices. It's just distributed systems. So scratch that. It's now just consistency agreements and distributed systems. Now, I started my career in a little bit of a simpler view of the world, where most of the applications I was dealing with were really just kind of full stack. Everything just runs in one single server and just it does the entire job. And so in those days, dealing with consistency was much simpler. So I'd have the app and I'd have the database. And when you wanted to make changes to that, right, you just have an update statement, update the thing, and then it would do the thing, and then come back. You could say, okay, did it write that thing correctly? And usually everything would work okay, right? As long as you've configured things correctly, it should all work okay, and everything was good. What if things got a little bit more complicated? What if instead of just doing one thing at a time, I was doing two things? So I'm trying to update two different records in the database. This was one of my first lessons learned as a developer, coming from just kind of doing kiddie demo apps. The first time where I did this, where I made the two updates and I read the back, everything looked okay, except if something went wrong during this equation. So I would do these two update statements, and then something would go wrong with the second update statement, and that was at first sort of realization of, oh, wait, this is partially succeeded, partially failed. And so, of course, the way we can manage this in a single system is to simply wrap that entire operation in a transaction. And now both of those operations either succeed or fail together. The whole ACID properties of the database ensure that this all succeeds or it all fails, and everything looks great. Now, my first sort of projects as a developer, everything pretty much looked like this. And we just had to make sure that when we were developing and writing stuff to the database, let's make sure we were wrapping things in a transaction. That was, of course, one of the things we would look at code reviews to make sure, hey, don't forget the transactions. But my next gig, I joined big corp IT, and that's when I realized that the real world is much messier than my simple systems where everything is just a single process and just the single database. So in this case, I was on a team that was an e-commerce platform, and my team was the cart checkout process. So that step where you click add to cart and place order, and then after you hit place order, some things happen in the background to actually make it work. That was my first introduction to the messiness and the complexity of distributed systems. So instead of having just this one single database that our app talked to, it was multiple databases. And so we had this situation where I would, write to one database, make an update, and then similarly do another update to the other database. So in this case, I'm setting the order status and then deducting items from the stock database because they placed this order. And I wanted to make sure that these both either all succeeded or all failed. So we wrap it a transaction, right? Boo. So the first time you try this, you start to get these really strange error messages where it's the error code starts with 8,000 and it's a bunch of other numbers after that. And it basically tells you, hey, in order for you to do this, you need something else on top of these databases in order to ensure that both those things either succeed or fail. And that, of course, is our friend, the Microsoft Distributed Transaction Boo. That's one of those things that, like, if you go to your ops person, the DevOps person, and say, hey, great news, we can do this whole like transaction across databases thing, but we just need you to enable this one awesome thing, the distributed transaction coordinator. And they'll usually hate you after that, because it's like we have to open up all these random weird ports. This transaction coordinator has to live somewhere to ensure that these two things either succeed or fail. Even with all that sort of stuff put in place, it does not have a bulletproof guarantee that both of these things will absolutely succeed or absolutely fail. It's not a being able to do a distributed transaction is not foolproof. So no, we can't do that. And that's, again, one of those things that you start Googling things, distributed transaction, and it's all these very sad Stack Overflow posts of like, here's all this crazy stuff you have to do to make it work. So that was my first introduction, trial by fire, and how do I manage these two updates across these two databases? How do I ensure that either they both succeed or they both fail? And so yeah, you get this error message saying you need to enable this dumb thing, the distributed transaction coordinator. So what is this? What is this thing, this distributed transaction? It's simply a database transaction in which two or more network hosts are involved. Now, technically, you don't have to be crossing the network. Even if you're doing like two databases on the same server and like you're also on that server as well, you still have to enable this thing. You cannot, without having this extra thing of a distributed transaction, you cannot have a transaction against both databases at the same time. This protocol, the most common one in order to achieve this, is known as two-phase commit or 2PC. And the way it works is this. We have resource A and resource B. There's two databases. We have our coordinator that is now this other thing to the side that is managing these two individual transactions. And it starts off the process in the first phase by asking each database to prepare a transaction. And now this is not actually going to commit the transaction yet. I kind of think it in my head as like I want you two people to go ahead and just put your finger in that data and just hold it there for a second while I go ask the other database if it's okay. And so they both put their fingers down on the data and they say, okay, yes, we can commit this transaction. So that's the first phase of the protocol, is the prepare phase. So each database then has to tell the transaction coordinator, can you commit this transaction or not? It's basically giving it a thumbs up or a thumbs down. And if the coordinator receives a thumbs up from everyone involved in this distributed transaction, then it's going to have the second phase of the commit protocol and then tell every database, okay, now go ahead and commit this transaction. But again, this is not a foolproof protocol because you can still have something going wrong with the second phase of the process. So I've asked both resources to prepare the transaction. They put their finger on the data. And then I say, okay, resource A, now you can go ahead and commit the transaction. And resource A goes ahead and commits it. Then I go to resource B and say, commit that transaction. But if something goes wrong in this communication here, somehow, then I can still have my system in an invalid state. Now, in the documentation of the DTC Distributed Transaction Coordinator and various other folks that have implemented this, basically they say, you can't ever let this happen. Like, don't do that. Don't ever let that little blow-up thing down at the bottom ever happen. And if you can guarantee that that never happens, then yes, this protocol works. But one thing that I know, years of building distributed systems, is that sort of Murphy's Law. Anything that can go wrong will go wrong. I think that's Murphy's Law, right? Yes. And when we're dealing with distributed systems, we have to realize that we can have network failures, we can have hiccups. Things can just blink off and on again, and nothing we can really do to absolutely prevent that. So we can still have the case where this can occur. Now, we may say, well, how likely is that to occur? And in systems where I've built these kinds of things, it would be something like the 5 or 6 nines of availability and uptime and guaranteeing these kinds of transactions. But every once in a while, a server would blink out, or more commonly, like someone updated DNS settings somewhere. Not me, someone else did that. And then something would break in this communication, and now I'm in this halfway invalid state. Now, there are people smarter than me that looked at this and said, what we need here is more arrows. And so we can have, instead of just a 2-phase commit protocol, how about a 3-phase commit or a 4-phase, and just keep asking things over and over again until everything starts working again. And the Wikipedia page on 2-phase commit goes into all these details of people have tried really, really, really hard to be able to have transactions between more than one resource, but eventually come to the conclusion that it just is never foolproof. It never is going to work 100% of the time. One thing you also notice here is that there's a lot more arrows, right? We've got another box over here to the side, this coordinator thing, and then we've got all this communication going back and forth. So this kind of protocol is actually much more expensive than just a normal database transaction. And some of our testing that I did in terms of I wanted to get rid of this transaction coordinator because it was such a pain to deal with, we saw that there's something like a 10x throughput decrease introducing this coordinator into the mix. So if I could do 1,000 transactions per second, now I'm down to 100. And that only gets worse the further these different boxes are from each other. Because I have to make sure that all these different communications have very low latency, otherwise it's just adding more and more overhead to the mix here. So even when I've put all of these things on one box, on one machine, it was a drop of 10x throughput in my transactions. And if I started to move these things further apart, then that greatly increases over time. So we realized, clearly we're doing something wrong here. What I would really love to do is just get rid of this thing altogether. We also found that this kind of arrangement really only works if you have explicit control over everything in your environment. You define the networks, you define the servers. If you try to do this in cloud-based environments, especially platform as a service-based things, it just doesn't work. Or if you try to do more fancy things in your database. For example, if you turn on the always-on feature in SQL Server, which is the most expensive checkbox in that installation dialog, if you try to turn that on, then it says, we can't do 2-phase commit anymore because we can't make these guarantees of this sort of always-on distributed nature. Or if you're in Azure or any other cloud provider, you use Azure SQL or whatever AWS is, I don't remember what it's called, then you don't have this ability to do this either. They will not, you can't call up Microsoft, Amazon support and say, hey, guess what? I need distributed transactions. Can you go ahead and open up all these ports for me? And they'll laugh and laugh, politely, I guess. So we can't do this in these sort of environments. But it also, depending on the resources, is less and less possible. So the distributed transaction coordinator is available for us if we use SQL Server and MSMQ, which again, the queuing technology we shouldn't be using anymore, but that actually does support distributed transactions. But as soon as I go to anything else in this equation, then there's no more distributed transactions. Or if we're doing something like a NoSQL database, like Cosmos or Mongo, something like that. So what looked really good on paper, or at least seemed good on paper, was having this transaction coordinator that can go against these different resources and would guarantee absolutely that the database transaction between more than one database would either succeed or fail. And so it can work in a single resource, but not across identical resources. So if I have 2 SQL databases, generally doesn't work. Disparate resources definitely doesn't work. And then depending on your database, we can even have the issue that inside a single database, it may not guarantee transactions across records. So I may not even be able to have a transaction against 2 rows in a database, depending on whatever that database is. So looking at, we basically came to the conclusion that we cannot rely on this 2-phase commit protocol anymore for these more complex conversations between distributed systems. So we looked at this and said, okay, how do I then address this problem? And so you start Googling and trying to figure out, how do I get rid of this 2-phase commit protocol? And so in distributed-based systems, in this example I'll be showing here, we are consuming messages from RabbitMQ or AMQP protocol. We'll have multiple writes to the database, and also producing messages, all within a single sort of transactional boundary of an activity. So it looks something like this. We've got C# code here, where I've got something where I'm updating an item in a database, and then I'm updating an item down over here, but that's a separate database. And then finally, I publish the message out to say, okay, this thing has happened, notify downstream systems that they can now go then do their further processing. So at this time, we're looking at, okay, we can't be the first people that have seen this problem in the wild of we cannot use this sort of two-phase commit to even do sort of a basic thing inside of a single application here. Luckily, I tend to, any kind of database stuff like this sort of thing, I tend to go look to see what Pat Hellens wrote about it, because usually he's already figured something like this out. And luckily for us, he did. He wrote this paper many years ago called Life Beyond Distributed Transactions. And I'm like, oh, that's what I want. I want to get beyond this thing. An apostate's opinion, which I had to go look up what that word meant, but it's someone who believes something fervently that no longer holds that to be true anymore. And the reason why he called himself this apostate is because he was one of the original developers and designers of the Microsoft Distributed Transaction Coordinator. So if like this guy that helped build and design that thing says we can't do this anymore, you notice too he worked at Amazon, so that's one of the reasons like going from Microsoft to Amazon, like, oh no, we don't do distributed transactions here. He's like, great, but we still have to have some way of coordinating agreements and consistency between these different distributed systems, these different databases, these different applications. So how can we have those kinds of guarantees when we cannot rely on this two-phase commit protocol? So in this paper, he had described this epiphany that he had, which was to assume a transactional boundary of a single, he calls it an aggregate or an entity. These aren't DDD terms, but just think of like a single record in the database. Assume a transactional boundary of that one thing. So if it's like, I don't know, Mongo, then it's like, assume a transactional boundary of a single document. If it's SQL, then a single row. And if you make those sort of assumptions that you can only talk to sort of one record at a time, then it forces you to coordinate activities between multiple different records in a different way. So he described this idea that if I have a transaction in one record over here, and I need to affect a change in a record over there, then I need to have some way to communicate from this record to that record somehow that, hey, you also need to do this thing, and that communication to that other record is also part of the same business transaction or database transaction of the original insert or update into the first record. So it looks something like this. We have these two entities, and by the way, right now it says messages flow. We'll talk about like what the message is, what is flow, and like how does this actually happen in practice. But the idea is that in my sending entity, when I write the data to the database, I also record as part of that this communication that I need to have then shuffled off to the other entity. So at that point in time, I'm not immediately doing any kind of like publish or send or anything like that. I'm recording the intent to do that thing sometime in the future via some kind of way of serializing that message into the database. So in his presentation and in his paper, he has all these like lovely diagrams of like, yeah, I just got this thing here. You've got these entities with these messages that remember them. We also need to make sure that in this picture here, we've got a message being sent from one entity to the other. We also have to make sure that the receiving entity does not perform that activity twice. And so this is known as idempotency, which is another great paper from Pat Hellen. Idempotency is not a medical condition. So in that idea, if I can only guarantee a transaction around this one entity, and I'm sending a messages to the other entity, I cannot guarantee that that message is only delivered exactly once. You either have at least once or at most once, but there's no exactly once messaging communication here. So I have to assume on the receiving entity that it could receive this message that from this other entity at least one time, and just assume that it could be multiple times that I'm receiving this message. So then how do I ensure that the receiving entity only processes the message once? So this is known as at least once messaging, at least once delivery, exactly once processing. And I'm always careful about making that distinction here because I do see like some message brokers that out there in the world, like we guarantee exactly once messaging. What they really mean is exactly once processing. So I just want to make sure that the receiving entity only actually does the side effect of this message the first time. So how do we do this? In our entities, the way we can manage it is an entity remembers the communication it's received. So not only are we storing messages that are outgoing to other entities, but when an entity processes a message, it's also going to keep track of that message to say, okay, when I perform this activity, let's go ahead and look up to see, have I seen this message before? And if I have seen it before, then, hey, nothing to do. We can just move on with our day. But if I haven't seen it before, okay, then actually process the message. So here, this lovely diagram of like, look, you got these entities with these messages flowing anywhere, and then I go look for the code behind this, and there was none. So I'm like, oh, fantastic. So he just like wrote a bunch of diagrams, but like didn't actually, like, here's an example of actually how to do this sort of thing. So I have had to implement this kind of thing myself in the past. I don't recommend implementing yourself because it's really hard to do and you'll probably screw it up. I know I did. So I'll also be showing some examples of third-party software that provides this kind of behavior out of the box. And then we'll dig into like the nitty-gritty details of actually how it works behind the scenes. Okay, so in my database now, I've got an aggregate or entity or record, whatever you want to call it. And this record includes my business data. So this is like the normal stuff you already put in the database. And it'll also include means of passing messages to the other entity. And this is known as an outbox. So like basically the whole point of this talk is the outbox pattern. But it is one of those things that you don't know that you need until you encounter a complex distributed system and realize that I've got all these sort of phantom updates or incorrect updates because we don't have these sort of distributed transactions. So the aggregates or the records include messages we want to send out the door in our outbox, and they'll also include that memory of messages I've received in the past. And we call this inbox. So some folks just call it the outbox pattern, some people have inbox and outbox, but we need both things. We need a way to communicate to other entities and save that data with our business transaction. But we also need a way to remember messages that we've received and processed so that when the next message comes in the door, the next time that same message comes in the door, we can have a way to check to make sure that we've already processed it or not. Okay, so where the distributed systems part comes into play is if we imagine that these aggregates are not just two records in the same database, but these are behind other systems. So there's like microservices or but there are other systems out there that we have to coordinate with each other, and we need to use this inbox and the outbox in order to coordinate any kind of activity between one or more of these systems. So, in this case, I've got my three services. The initiating service is service A, and then the receiving services of the side effect are going to be B and C in this picture here. So when we were looking at the distributed transaction coordinator, we had this coordinator thing that was this external service that was managing the communication and the two phases of the two-phase commit protocol. So we still need something like that here in order to dispatch messages from entities to other services. There's nothing in our databases that will just automatically do this. I know SQL Server has like, what is that, the broker? No. It had like some messaging thing built into it too, but please don't use that. So we need something here in order to facilitate taking messages out of these records and then passing them through to these other services. So we're going to do that via dispatcher. All right, so the way this will work is it first starts off with a transaction with inside service A. And so in that service, we will write the business data like we normally would, but then we're also going to, in our same database transaction, save the messages that we're going to be sending to the other services. Now, the way those messages look behind the scenes, they're not going to be exactly the same as like an AMQP message. It'll just be some basic information about here's the body of the information, and potentially here's the destinations where this message should be sent. So we have to make sure that our database can handle that kind of unstructured data. I've used this kind of pattern in pretty much every kind of database. So yeah, if you need to store it in a JSON column, or if you need to put it in a separate table, whatever that is, we just have to make sure that we can transact both of these things together. Okay, so that transaction succeeds. So this initial service is done with its work. In its view of the world, it is good. Everything is successful in what it's been trying to do here. So once that transaction succeeds and can no longer be rolled back because it's been committed, now I need something to then take those messages out of these entities and then pass them along into the other subsequent services. And so that's going to be this dispatcher. This dispatcher will look for unsent messages in the outbox of the first database, and then it will translate those to on-the-wire messages. So I will translate whatever was stored in the database into an actual on-the-wire AMQP message that will then be sent out to any other services that then need to be involved in this overall business transaction. Okay, so I take the messages out, I read the messages out, and then at this point, I can then pass them along to each individual service. Now, each individual service here is also in its own individual system, its own individual database, and it'll also have its own individual transaction boundaries. So at this point, microservice B receives the message. It will transact the data, so it will do the changes it needs to do in its business database, and store that message that it received in its own inbox table or inbox record. So at that point, that all succeeds or that all fails. But again, service A has already left the picture. We don't worry about service A anymore. Now we're only dealing with service B. So in this kind of picture, I'm drawing more arrows here. We also want to think through the different failure modes of what can go wrong in this kind of operation here. Now, in the two-phase commit protocol, it basically says in even Wikipedia, you cannot let these protocols fail. If the protocol fails, then you no longer have these guarantees. So the only way this can actually work is if you can absolutely guarantee this. But in our scenario, we can have all sorts of failures here because I'm only dealing with one service at a time. I just need to ensure the system can recover in the case of any kind of failure here. So what happens when things goes wrong? When things go wrong. Now, I'm also very deliberate here when I use the word when, because if you use the word if, as in if things go wrong, then most people get happy ears on, and if, well, that's such a remote possibility that it probably will never happen. But everything goes wrong, right? How many times has a certificate error brought down some cloud provider? Or some DNS error brought down an entire cloud provider? These things still happen. And so if Microsoft and Amazon and Google cannot keep their stuff up at all times, then I have no chance. So I will just assume that things will go wrong and plan accordingly. So back in this picture, service A is done, service B is done, and now I'm going to service C. So what happens now when service C has some sort of failure? What could the failure be? Doesn't matter, really. It could be down, it could be unresponsive, there could even be an error just in the configuration of the network, so I cannot successfully dispatch this message to that other service. Now, because these messages are durable in my broker, then I have some failure recovery mode sort of built in already, because it's not like an HTTP call where if you are making the call and the other side's not listening, then you kind of lose that HTTP communication altogether. Because I've got my messages stored in a broker, then that also means that if something goes wrong, then I can retry that message. So in this case, we have some way of storing the messages we need to retry in another, typically it's in the broker itself. And then we can retry that message again. We can try to dispatch that message again to our other service. So in retries, Again, we cannot guarantee that messages have been delivered exactly once, so we want to make sure that they are processed only once. So if I'm retrying this message I've pulled out of this dispatcher, where I go, okay, let's go pull the message out again, and let's go re-dispatch it to the other services. In this case, microservice B here has already seen this message before. And it knows it's seen that message before because it stored that message in its inbox table in its database. And so for it to process the message, the first thing it does is look up in its inbox to see, have I seen this message before? And if I've seen this message before, then nothing to do. We can just move on with our life, and we don't do any business data manipulation here. We just successfully process the message by doing nothing. Now, service C has not seen this message before, so then it will go ahead and do its business data transaction and store the incoming message in its own individual inbox. And now, everything has succeeded in terms of boxes and arrows on a screen. The mechanics of this are quite a bit more complicated, as you can imagine, or I didn't imagine, and then I tried doing it, and then I imagined, after seeing a lot of failures from the edge cases here. But we do have to worry about things like you can't have infinite memory. We cannot remember every message forever. You can say you can, be like, yeah, just stick it in a Kafka stream somewhere. But even like Kafka's default behavior is to only keep, 7 days or something of messages and streams? And so we cannot store business data and every possible interaction, because that will just grow unbounded over time. And so we have to have a way to forget messages after a certain point. So I won't be covering it today, but that is a thing you have to worry about in this sort of pattern. You'll realize quickly that if you store every interaction, then your database will just explode in terms of size. This also doesn't tell us necessarily how to deal with oh yes, I forgot the last step in this process. Once I've successfully dispatched the message to the broker, I can now remove that message from the outbox of the originating service, which again is its own individual transaction. So in all these different interactions, I'm also trying to think through what happens if the process fails right here. What happens if the process fails right there? What if the process fails right here during the removal of that from the item from the outbox? Let's say that transaction failed. Then it'll retry to pull the message in the outbox, and now all the downstream services have already received and remembered the message. And so again, the side effects then only happen once. Now, the next part is there's a bit more challenging part. This kind of mechanic is a technical challenge. And it's kind of fun to do because with these kind of infrastructure sort of stories or features that you develop, they're fun because you're your own product owner. So you get to decide exactly what gets done. So I did have fun building this kind of thing, but the next complicated part was what is the nature then of this communication between these different services? If I cannot guarantee that this entire operation succeeds or fails, I then have to design the communication and the interactions, the conversations between each of these different services. Now, there are a lot of different patterns in this space. There used to be just one description of one pattern, but as more and more people were doing these kinds of interactions, you will start to see a lot more descriptions of different ways of modeling these sort of interactions between different systems. So we have things like a routing slip that you can use to have a message flow between different services. You can use something like a Saga to have a long transaction broken up into smaller transactions. And then we also will use something like a orchestration or choreography via process manager to be able to tie all these different things together. But the very first thing we have to do is describe the conversation between services based on kind of real world business requirements. And so the example we'll be looking at today is going to be complex agreements and conversation patterns via Sagas. Now, there's a bit of an overloaded term in here, so the .NET folks have a different thing called a Saga in our land. This is really a process manager. The Saga I'm talking about here is the original OG Saga definition, which is a complex transaction that is, we cannot have in a single bounded transaction. We have to have that complex transaction broken up into a series of smaller transactions. And the canonical example here is, I should update this because no one does this anymore. Like no one calls a travel agent to like book a trip, right? Wait, that's not a thing we do anymore. But that's the idea, is like, if I want to book a holiday, then what I will do is, for every one of the things I need to book as part of that, each one of those is in its own individual transaction, right? So I book a flight, but I book a flight going to the flight website and booking it through there. And then I go to book a rental car, I'll go to the rental car website and book that rental car there. And finally, if I get a hotel, then I'll go to the hotel website. But those three different resources are not like transactionally bound to each other. And in fact, like that would be almost impossible, right? If you were to imagine, how would you do this kind of operation using a distributed transaction, using two-phase commit protocol? That means we'd have to get in a Zoom meeting, get the flight person on the phone, the rental car person on the phone, the hotel person on the phone, all in one synchronous Zoom call. And I'm like, all right, we're going to book a trip. Rental car person, can you book this car? And they're like, yes, I've had my finger on the car. Hotel person, can you book this hotel room? Yes, I'll put my finger on that room. They go to the flight person, can you book me this flight? Yes, I'll put my finger on the seat, I guess. And then if all of those people can agree that we can do this transaction, they'll say, okay, book it, book it, book it. But we never do that, right? We don't do that kind of like complex transaction, usually in the real world. I do have this sometimes. If anyone here has like bought a flat or house or sold a flat or house, you have this agent that is doing the job of the transaction coordinator. They're like, okay, right, buyer, do you agree on this price? And do you have your deposit? Yes, okay, but they'll put the finger on the check. They'll go to the seller, say, hey, do you still want to sell this property? They're like, yes, okay, finger on each of these two things. Now we'll exchange the check or whatever it is. And I usually have to like go to a conference room or some office to conduct this transaction. So there are cases where two-phase commit does happen in the real world, but it's a pain. Right? It's such a pain to have all this communication coordination. And the idea with the Saga is that instead of us trying to coordinate all these different things together, instead what we'll do is have each step in the process both having a forward transaction, which is to do the thing, but also have a way to undo the transaction. This is not the same as a rollback. Like the transaction is already committed, so I can't roll back what has already been committed. Instead, what we have to do is find the logical undo from a business perspective of reversing whatever that first operation was. So in this example, I say, book the flight, book the hotel, book the car, but if something goes wrong with one of those, then instead of me like rolling back the transaction, we find, well, what is the logical undo for booking a rental car? Well, it's to cancel the reservation, right? So we cancel the reservation for the rental car, we cancel the reservation for the hotel, and the system is back to its original state. Maybe. So one thing I liked about Sagas is when we're designing interactions from a business perspective, it's not necessarily the case that the systems has to go back to the exact same state it was at the beginning of the transaction, because these are all now business requirements. This is like policies, like the terms and conditions sort of stuff. So in this case where we need to book a rental car, it may not be the case that the rental car allows us to cancel reservations. Or they allow you to cancel a reservation, but they'll charge you for it. It's like, here's £10 for canceling the reservation. So like your bank account is not back to its original starting point, but like the reservation has now been released. So as we're going through this sort of design process, a lot of these questions are not technical questions, they're more business questions about how should we handle this kind of situation here. In the case like we need to be able to, like if someone reserves a car, we need to have some way to unreserve it or cancel the reservation. So we have to build that capability into our system to be able to perform these kinds of operations. Not everything is cancelable either. So Sagas are great if you can cancel operations or have some way of rolling things back, but that's not always going to be the case. There are going to be some resources where you can't undo those things, and I did a whole talk on that as well about, there's some kinds where we can't undo an operation or retry it. We just may have to be like, I can't do anything about it. So good examples like if one of my resources is like SendGrid, I can't unsend emails. I can send an apology, which is kind of like an undo, I guess, but I can't unsend that thing. So there are going to be cases where this kind of pattern will have some operation where we can't undo it, and we have to just decide, how do we want to handle that situation? All right, so my real-world example here, I was having to, this is something from a project I was working on, was this e-commerce system where initially they had that single block of code that was like, save the order, update the stock, publish event. That was the original code. And something that the developers I was working with didn't realize that they had unknowingly entered into the messy world of distributed systems because it looks so easy to code when it's just like call an API, publish the thing. But in reality, it's much more complicated. So we had to walk through these scenarios of saying, like, what happens if I have failures at each point of this process, and how can I mitigate those sort of things? So anyway, it started out with this original business requirement about the order. It says the order can be fulfilled when the request is approved. So like I approve the order based on that's a valid address, that's a valid phone number, it's a valid email. It's not a country we don't want to ship to anymore, that sort of thing. So when I approve the order request and I confirm the stock, that's when the order can be fulfilled and finally shipped out the door. Now in this case, we have these different systems for each of these different items. So I've got an order request system, I've got an order fulfillment system, and I've got a stock system. And I need to design communication between each of these different operations in order to fulfill that business requirement of when the order is approved and when the stock is confirmed, then you can fulfill the order. So when I'm going through this process of designing these interactions, I imagine that each one of these boxes in my distributed system is a human being. And say, well, if these are people talking to each other, what would be their communication back and forth in order to be able to fulfill this overall business requirement of these different systems having these different data? So in our case, we have the order request, which is the thing that's, when you click save on the website, that's what gets saved as the order request. And now I need to notify the order fulfillment system, hey, an order's been created, go ahead and start the next part in the process. Now I could, in this very first interaction, we have to decide what is the nature of that communication between the order request system and the order fulfillment system. We could use API calls, but again, if I do API calls, then I have to worry about what if the API is down. But typically for these kind of async sort of scenarios, instead what I'll do is leverage messaging. So okay, great, let's do messaging. What is the message? What should the message say? What should it imply? What is who owns the message? What is it describing? So I could do it to where I say the order request system tells the order fulfillment system, hey, start fulfilling an order. But if you're people, these are human beings, the order request person, the order fulfillment person, they probably don't like being told what to do. And no. You just tell me, you just notify me when something happened on your side, and then I decide what to do on my side. You don't get to tell me what to do. So instead of a directive or a command to this other box, instead I will notify that other system via an event. So this is going to be our order created event. The order request service system, when it saves that order to the database, at that point in time, it will also persist that order created event into its outbox. So I've removed all the little envelope-looking things and all the different queues and stuff. So now it's just sort of a macro level of how do we do this communication here. So the order request system notifies the order fulfillment system, hey, an order's been created, and now you can go off and do whatever you need to do. So the order fulfillment system, the little text just went from over there to over there. Behind the scenes, this is using a message broker and outbox to be able to do that communication, to guarantee that I will have that communication flow from the order request system to the order fulfillment system. All right, so now the order fulfillment side, it's going to look to see, okay, I've got a notification that the order's been created. Now I need to validate the stock. But that's in a different system. That's in the stock system. So I'm going to ask the stock system to hold the stock for this order fulfillment process. So I will say, hey, I need stock request for this SKU, for this SKU, and this SKU for these quantities. And then the stock system receives each of these requests, and then we'll put the stock aside, reserve the stock, in order to fulfill it at some point in the future. Now, stock system is not responsible for knowing when to ship or not. It knows how to put things aside, but it's still relying on the order fulfillment process to finally notify, hey, now you can go ahead and confirm the stock or release the stock or ship the stock, whatever. Okay, so stock receives these requests and will then communicate back based on the feedback it sees from its system, do I have enough stock or not? So let's say stock confirmed, yes, stock confirmed, yes, stock confirmed, yes. Again, individual transactions going against its business database. Each one of these messages then stored in its own individual outbox before being passed along via this dispatcher to the downstream service. So again, on this diagram, it's just like boop, 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 boop. But behind the scenes, outbox, inbox, all that sort of stuff. Okay, so now the order fulfillment system has received confirmation about all the different stock requests. And now the order fulfillment system is just waiting for the order request to be approved. The order request system, I don't know, you click a button and you say confirm order, whatever. Again, via a notification, an event will notify the order fulfillment system, your order has now been approved. So now that I have successfully confirmed all the stock and I've also confirmed that the order's been approved, now I can fulfill the order for whatever that means. I don't know, publish another event that maybe the shipping service then picks up and actually pulls the stock. I don't know, but we will notify someone else that the order fulfillment is successful and we can now ship this order out the door. So order request says, okay, if order fulfillment successful, we'll update the status of our order request to fulfilled, and the business transaction is now successful. Now, this is a lot more complicated than everything in a database, right? If I just had a single database with just different tables, maybe different schemas, I could just do one transaction to do this entire operation. But as soon as you start moving things apart and distribute them, now we have to design a conversation and communication between these different services in order to fulfill the overall business need of, or the overall business rule of, an order can only be fulfilled when it's been approved and the stock's confirmed. Now, with this picture, originally, I could have this single transaction look at all the data all at once, but now I can have this sort of partial success or partial failure. In that case, we would be looking at order cancellations. So an order can be canceled when the stock is denied or the request is rejected for whatever reason. Again, this is not something I really had to worry about when it was in a single database transaction, but now, again, I have to now design the interactions of how do I manage these partial success, partial failure scenarios and be able to get things back to where they used to be. And so that's this part. The next part here is the reverse side of the Saga implementation. We did all these success paths of saying, stock confirmed, order approved. Now we got to go the other direction is what happens when one of these things goes wrong. So first one up is order can be canceled when first the stock is denied. And even here we can have a partial success and partial failure. Some of the stock can be confirmed, but some of it can be denied, and we need to be able to handle those more complex scenarios. So in this case, we've got our back to our stock requests over to our stock service. The first one succeeds, the second one succeeds, the third one does not succeed. It failed successfully, which was the request was denied. And so the order fulfillment service receives this feedback that 2 succeeded, but 1 failed. So to deal with this scenario, I have to go back and look at what is the logical undo from a business perspective of whatever has succeeded so far. So in this case, I've got the order request. I haven't heard from the order request yet. So it could have been approved. It could not have been approved, but I can't tell that from my vantage point in the order fulfillment side. So I will just notify the order request service to say, hey, you need to cancel this order because reasons. So that will take care of the order request side. For the stock side, we have to look at what is the logical undo of confirming stock. Well, in this case, we can return the stock. So in this communication, we'll have a cancel order request sent to the order request service, and then stock return requests to the stock service. From a patterns perspective, this is starting to blend events and request response via messaging, and that's okay. That's a lot of what I'm doing when I'm whiteboarding these kinds of interactions, is going through like, well, does this make more sense to be a request or an event or a command or request reply or a command? What is the right kind of interaction here? And we will draw these different interactions out and just kind of take a step back and say, does this make sense? Like if these were people, human beings performing this, would this make sense in their heads? And there's not necessarily like exactly right or wrong answers here. You'll also run into trouble if you just say, every message between every service must be an event, which can work for a lot of scenarios, but there's going to be cases where publishing an event in order to enact change like makes the interaction really messy. So I'm looking at like how messy is this interaction, and does it kind of make sense from a business perspective? So I send a request to the order request service to say, go ahead and cancel that order, and stock service, go ahead and return that stock. And then each of those process each of those in turn. So now it's back to where it was before. It's like the overall system's state is not exactly to where it was before at the beginning of the saga, but we have to look at that from a business perspective about what makes sense from a requirement side that we would need to then kind of get things back into a good state. So a canceled order is like not a happy state for the customer, but it's at least not having stock sitting on the shelf being held forever because that order will never get fulfilled. All right, what about the other side here? An order can be canceled when the stock is denied or the request is rejected. So again, I have this scenario where I don't necessarily know the current state of everything, so I have to be able to handle these sort of edge cases here. So in this case, I get an event from the order request service saying order's been rejected. The order fulfillment service then goes and looks at its knowledge of where things are. And so if the stock has already been confirmed, all of it, then I need to go tell the stock service, go ahead and return that stock. If it's not been confirmed yet, then I may need to wait to get notified from the stock service about what the state of things are. You could probably like just put an API call in there, I guess, to just ask the stock service what the status is of things. But again, there can be problems with that because messages have a way of being processed like asynchronously, which could mean like a day from now or a week from now, hopefully not a week from now. But there's no guarantees about when that timing of when that message will be processed. So I have to be able to handle these kind of like muddy, messy situations of not exactly know the state of everything and sort of wait for the information to come into me before I then go and make decisions in my service. So in this case, let's just pretend that all the stock has been confirmed. And so now I'm sending out notifications to the stock service to go ahead and return all that stock, and everything is successful. Well, like we're back to where we were, kind of. The order's been canceled, but I guess the order was rejected. But at least like we haven't put aside stock that will never be fulfilled here. So from the customer perspective, maybe it's not a happy ending, but from my system, overall business system perspective, we are back to where we started it from. All right, so I was going to show a code example of this, all these different interactions. And I will be showing this via, where is my JetBrains writer? There it is. Is that big enough for the folks in the back? Yes. Can the gray hairs put thumbs up too? Yes. Okay, good. So this is the initial interaction here. This is the action to go ahead and post to post up your shopping cart data, and it will create the order for you and then do downstream stuff. Initially, this was it was save stuff to a database, and then publish a message out the door. Now we're just doing the one thing that we can guarantee. In this case, I'm in the orders service. Yeah, over here. And now the event I'm publishing out, this event right here is that order created event that we described in this initial interaction. But now, when I'm publishing this event, it will not actually publish this event right this second. So even though it says await message session.publish, behind the scenes, that will actually be temporarily storing that message in our database. before it actually goes out the door to be able to be sent to the downstream systems. Now, the way I enabled this was initially I had my own version that did all this stuff for me, but that's a lot of infrastructure code to manage. And so in this case, I'm using a product called In-Service Bus. Those folks are here, over there somewhere. So if you want to learn more about the details of how they implemented this, you can go talk to them. But the way I enabled this in my system is actually very straightforward. I just had this, enable outbox, and that was basically all I needed to do. So this is not an easy thing to be able to do yourself. So I would encourage you to look for third-party libraries to help you do this for you. So in .NET land, like In-Service Bus does this. Mass Transit has this feature as well. What other ones out there? Rebus, I think, also supports this. What other buses out there? Well, at least those are the most popular ones, at least that I know of. We do have to do some additional configuration that our broker, or this bus library, does need to have a connection to our business data. And so in this case, I was using RabbitMQ and Cosmos, because why not? So I have to tell the broker, this is how you connect to my business data, and inside of that database, it will create the structures it needs to be able to store the messages in an outbox. So behind the scenes, there will be an outbox table that gets persisted there. And then finally, when we have the actual processing of this, the order fulfillment, so we had this order created event. This order created event is a message owned by the orders service, because it owns the business knowledge of when an order is created, so it owns this message as well. That's over here in my order contracts. There's my order created event. And inside of it, it's got some kind of basic set of information. It has the ID of the order, as well as the list of line items that you're going to get purchased. That's for that as well. So that event gets published to the order fulfillment Saga. Now this is called Saga because it implements the Saga pattern, but in In-Service Bus, this is a process manager. That's what this thing is. It's a code level representation of a process manager. So in my process manager, I will have all the messages that I need to worry about in terms of managing this overall business process. And so that's what all these different I am started by, I am handled, blah, blah, blah. These are all the different events coming in that we need to manage inside of this overall interaction. So it starts off with just handle. And we, out of the gate, we had to worry about, well, what happens if I get this message more than once? What if the order's already been canceled? Because I could have received order canceled before order created. Like that can happen, and we need to worry about this in these sort of async scenarios. We capture all the information here, and then we said we needed to send stock requests over to the stock service. And so that stock request message has the order ID, the product ID that you want to order, and then the amount you've requested. This message is owned by the inventory service, and so it also has messages back to saying stock request confirmed or stock request denied. So as I get information in from these other events saying order approved, what I'll do is I'll keep track of what things I've, from a business perspective, I'll keep track of what I've received here, and then process the business logic of can I fulfill this order or do I need to cancel this order? So here I have if I've canceled the order, then I got to process the cancellation, which is complex stuff, but basically cancel the order and return the stock. And if it was successful, check for success. Well, I can't be canceled, so this order can't be canceled, that is. And we had that business rule that says an order is, we can fulfill an order when all the stocks are confirmed and the order is approved. That's represented by that line of code there. And then if both of those things are true, then I can publish out order fulfillment successful. But all of this started out with the whiteboard diagram, or Miro, whatever. So we are designing these interactions. So it comes time to the code. This is actually pretty simple. The complex part was designing the conversation between all these different systems and services. All right, so let's go and wrap things up here. All right, So in order for us to enable this transactional outbox inbox pattern, the first thing we have to do is find where the transactional boundaries are in our system. Based on each database, what is that transactional boundary that it has? So in SQL, for example, like we can do multi-table transactions. And so in that database, we'll have an outbox table and an inbox table, although you can combine them, that will have the messages that need to send out the door, and we'll also store the messages we've received. All right, so just some final lessons here. Our picture became much more complicated with all these different things going around the scene. So this kind of distributed system interaction is much more complicated than we had before. But if you're in the situation where you're kind of forced into the situation of being in a distributed system world, then we need to be able to use these kinds of patterns to help guarantee that these overall business transactions can succeed or fail. So final lessons learned. Distributed transactions are, quote, easy locally, right? I can do distributed transactions on this laptop. But they're hard or / impossible when you're actually distributed, which is ironic, right? It's actually really, really hard to do distributed transactions in a distributed scenario. So instead what we'll do is find the transactional boundary of each of the different business data items in our distributed system, and then use outbox and inbox patterns to coordinate the communication between these different services. So if y'all have more questions about this, I'll be hanging around afterwards at the in-service bus particular booth, so we can talk more outbox, inbox junk. Otherwise, I hope you'll have a great rest of the conference, and thank you for coming.